and charging infrastructure for electric vehicles. Workshop series organized by IEEE Y2N Pro. To give a brief overview of this workshop series, this is a comprehensive set of workshops that offers both theoretical and practical insights into battery technologies and charging infrastructure of EVs. This series addresses the surging demand for expertise in the EV sector, focusing on battery systems and charging infrastructure. You will be able to explore the evolution, operational principles, and future advancements of EVs, delving into battery technologies and innovations aimed at enhancing efficiency and safety. Getting back on today's workshop, it will be on the area of advanced BMS algorithms, focusing on AI and machine learning integration. Before moving on, we have some important announcements to make. We have already shared these guidelines to follow during the workshop series. However, I will read the guidelines and make sure that you follow them for a smooth session. A quiz would be administered at the end of the workshop series, where you would be assessed on the knowledge gained. The IEEE credential certificate will be awarded only if you achieved at least 80% on all such above-mentioned quizzes and attend at least 80% of the sessions. Attendance will be marked at 3 given instances of the session. Therefore, please be present throughout the session. Please rename yourself using the registration number provided in the handbook and your name if you haven't done so already. Today, we are honored to have a distinguished academic with us who will guide you through advanced battery management systems algorithms. Thank you, sir, for accepting our invitation and joining us today to deliver the keynote speech. Dr. Logeeshan is a dedicated researcher and academic currently serving as a senior lecturer at the University of Moratuwa. He earned his bachelor's degree with first-class honor in electrical and electronic engineering from University of Moratuwa in 2015. He then completed his PhD in electrical and computer engineering at North Dakota State University in 2019. Dr. Velmanicum's expertise extends to AI and IoT applications, smart sensor development, finite element analysis, and renewable energy solutions. Apart from his academic career, he also actively contributes to professional societies, including IEEE and IESL. Moreover, he holds leadership positions in these professional organizations and academic communities, demonstrating his commitment to advancing interdisciplinary research and innovation in electrical engineering and biomedical applications. So, ladies and gentlemen, please welcome Dr. Logeeshan to deliver this keynote speech on advanced BMS algorithms. The spotlight is yours, sir.
Hi, thank you for the wonderful introduction, Yasiru. So, shall I share my screen?
Yes.
Okay, sure. Let me share my screen. Right. I hope you can clearly see the shared screen. Am I right?
Yes.
Cool. Right. Let me make sure I have 2 screens. I will make sure everything is right. All right. You are seeing the presentation view. Am I right?
Yeah.
Yeah, cool. Cool. Okay. So, good evening, everyone. So, thank you, Yasiru, for the introduction. And myself is Logeeshan. Already everything is mentioned over there. So, I just want to say I am not a battery expert, right? But I got a chance to work with a professor in University of Maryland. So, I will let you know who is he. He is an expert in battery, right? So, after that, I started to use that battery data to do certain researches in the AI domain, right? So that is the one accurate prediction of remaining useful life for lithium ion battery cells using deep learning neural network. So that is the project that I'm going to talk about. So this is an undergraduate project which is supervised by me and co-supervised by Professor Michael. So that's the project that we are going to talk about. If we get some more time, so I will talk about another research that I have done on research related to sense anomaly detection in battery energy storage. So it's based on the remaining time. Okay, so let's go into the seminar today. So imagine you are driving in a highway in your electric vehicle when suddenly your car falters due to the battery failure. The uncertainty of battery life isn't just an inconvenience, it poses serious safety risk. This brings us a critical issue: the aging of lithium ion batteries. So, to overcome these issues and find a solution, how we can estimate the remaining lifetime of the lithium ion batteries, especially when it's come to EVs, then we can easily say, okay, this car battery have used this many cycles and this have remaining lifetime of this many cycles. For example, the Nissan Leaf market in Sri Lanka, right? So the second hand market is really, really low because most of the customers do not know how long the battery is used, how many cycle it was charged, and they don't know whether it's replaced with a new battery or not, right? So the new batteries are there available, but if you order it from China or some other countries, whichever the battery comes over here, those are not original one. So when you replace a new battery into the Nissan Leaf existing battery system, the BMS, battery management system of the Nissan Leaf, get confused. So it loses its cycle counts and everything, right? So therefore the remaining lifetime is always a question. So if you are using the original battery with the BMS system from the beginning, the BMS system have an ability to count how many cycles we have charged, how many cycles we have discharged. All this information will be there. But in any case, if a person replacing the battery, at that point, the BMS system fails, right? So therefore, we do not know whether the battery is replaced or original battery is there. So always a risk to buy a Nissan Leaf car in second hand. So I know a professor, he will be also doing a session over here. He's owning a Nissan Leaf car, which is a 25 kilowatt battery, where when he purchased that car, it was able to run 95 kilometers with AC on, right? For one single full charge. But nowadays it's reduced to 50 kilometers. So when he tried to order the battery, he found out there are no genuine batteries available in the market. If you try to order it from China, most of the things are not that genuine. Okay. So how we address this issue? So how we make sure when you are going to buy a car, second-hand electric car, so the battery is actually used this many cycles, or this many cycles are remaining, so you can use for this many charging cycle and discharging cycle. So in that case, we will get a clearer picture. Okay, so I'm going to buy a car which have this remaining useful lifetime. So let's buy it and use it. Whether it's worth the price for the second-hand market, can I run this many years with this many kilometers? So all this can be estimated if you know the remaining useful lifetime of the lithium ion battery cells. So that is the talk going to be today. Okay. All right. So let's move on to the next slide. If you have any questions, please feel free to type it in the chat, or feel free to unmute yourself and ask the question, or raise your hand and ask the question. Okay. All right. So he is Professor Michael G. Pecht. I'm not sure how many of you have know him. He was here yesterday in Sri Lanka. So he is the keynote speaker of Mercon conference that is arranged by University of Moratuwa, and he is the honorary chair as well. He is like 73 years old right now. He has 58,711 citation. I don't know anyone in Sri Lanka has this much of citation level. And the H index is 108. So that means when you are doing a research, these citations and the H index values a lot. So it tells how good you are a researcher. as a researcher you are, right? So he is an extraordinary person when it's come to reliability studies of battery and many other microelectronics. So I got a chance to work with him. Actually, I requested for a battery data. I saw a paper that he has published. So then I requested him for that data. So from that point onwards, we got connected and we started to use his data. It's in the open domain. You can go ahead and you can simply identify this link, right? So this link over here, you can find all the data available related to the battery. Open source, he put everything. So we have used his data to develop certain system related to battery management system, right? So one research is this one. Another research I will talk at the end of the lecture very briefly to give you an idea. Okay. So he's Michael G. Petched. So he brings close to $6 million every year to his research lab. 150 big companies, including Intel, Tesla, Samsung, Philips, and all the big battery manufacturers and all the companies sponsor him to do the research. So he's a really, really big shot, right? And the good thing is the data is freely available in this website, right? So I use this data into AI to do certain prediction and some analysis using battery related stuff. Okay. So he's the person. Please feel free to visit this one and read about that thing. Right. So if you have any doubts, please email him. He's really, really fast in replying. He will get connect to you and you can have a wonderful discussion with through the mail itself. You can mention my name. I did a lectures on this thing, which is related to the research or something. He will definitely respond to you. Okay. So with that thing, I will move on to the next slide. So we will just put a base information. Okay. What is the benefit of having an electric vehicle versus a gasoline vehicle? I believe that will give a foundation for us to understand better. So let me share my computer sound also because yeah. So I'm going to play a video next. Okay. So if you see the electric vehicles, there is no greenhouse gases released, right? So the energy is coming from the utility company. Basically, most of the cars, including Tesla cars and Nissan, will be able to produce more than 100 mileage range, right? Even the three-wheelers in Sri Lanka that they are converting into an electric, they promise 150 kilometer for full charge when the battery is new, right? But the negative aspect is it will take a long time to charge, right? So that is an issue when it's come to charge. And the cost is very less. It's only 2 cents per mile. At the same time, if you take the gasoline, it's not good for the environment coming from the petroleum industry. But for a full tank, it will be able to provide 300 plus mileage range. But to refuel, maybe less than 5 minutes, you just go to the pump station and fill it up. So, but the price is 6 times higher than the electric vehicles. So you can also ask a question. So the battery, always these questions, I saw it as a memes in everywhere. So the battery is there. So we waste a lot of gases emission over here in the diesel power plant, coal power plant, and all the other fossil fuel related power plants. Again, we are getting that electricity, charging our battery, and we are running the car. So anyway, how it's going to contribute for the environment, right? The thing is, it is going to contribute for the environment much more efficiently because the diesel generator or the fossil fuel electric generator are much more efficient than a car engine, right? So therefore, while you fill the car with the fossil fuel and running it, you are going to get a certain percentage of the efficiency from the engine. But if you use the same fossil fuels to the electricity generation company, the efficiency is really, really high. So in that case, you are going to generate the electricity with high efficiency and you are going to transmit to your home and you are going to charge the car and you are going to run on the road completely. It's fine. It's not going to emit any gases. So it's environment friendly. right? So that's the thing. Mainly when it's come to electric car, we know that is cheaper and it can travel for a longer distance. Nowadays, with the current battery technologies, lithium ion batteries, it can go for a longer distance. Certain cars even claimed they can go for 300 to 400 kilometers in Tesla cars for one full charge, right? But there are negative things available. So when it's come to after a certain thousand mileages, then the battery started to degrade, right? So then the mileages started to drop. So when you try to replace a battery, it's really hard and it's costly, right? So especially in country like Sri Lanka, we cannot get those batteries, reliable batteries. When I say battery, there are batteries available, but reliable batteries. So that is a major issue. So in one of the keynote sessions, Professor Michael said, the person who is from University of Maryland that I'm collaborating with. So most of the batteries that we are using right now in Sri Lanka and all over the world are not original batteries. Those are batteries manufactured in somewhere as a household job in China and some other countries, and they wrap it up with a new label. That's all do. They take the old batteries, which have a certain number of voltage, can hold a certain number of SOC, then they get it, wrap it with the new wrapper, and they are shipping it to the countries. So which are not the original ones. If you find a battery in Sri Lanka saying Philips, there are 50-50 chances it might not be original Philips. The reason behind it, the people got an old battery, wrap it with the Philips thing, right? So to distinguish this one, so which is the original one, which is the local one, there are certain parameters. So we have to break up the battery, internally see the battery arrangement. So each battery company, reputed battery companies have their own structural architecture for the cathodes and these, what is that, plates and everything. So based on the structure only, you can identify whether it's original Philips or not. But when it's come to appearance, both are same. So we cannot trust those issues, right? So those batteries. So that is a big issue when it's come to Nissan car. And it's expensive too, the batteries. So that's why the second-hand market went really bad before these economic crises in Sri Lanka. So you can simply find a Nissan car for 12 lakhs, right? Which is second hand, right? 12 lakhs. It has comfortable in a space and all the functions are working. Only issue, it cannot travel for a longer distance, right? So still it's there in many cars. Many people keep their Nissan car, don't know what to do with that thing, cannot sell because it gives only 50 kilometers. Maybe they are using it for going to a supermarket, buying stuff, that's all. So in that case, it's not worth to have an electric car, especially in Sri Lanka. So how to overcome these stuff? So that's how what we are going to address through this research part. Okay. So if you take the main components of the electric car, these are the things which is already covered in the video. So we have charging port, transmission, and onboard charger, auxiliary battery, transition battery pack. So we have two. Auxiliary battery is the one which help us to start the car, right? It's the thing, the typical battery that we have it in the petroleum, like gas, diesel cars and petrol cars as well. So this is the battery that we have it over here in the back underneath the surface. That is going to be our main battery, which is charging while running. So thermal cooling system for the battery, right? We don't have any engine. So for the battery nowadays, there are Nissan car uses the airflow to cool down the batteries while we run it. But certain cars, especially Tesla, certain models use liquid cooling technology to cool the battery because it's heated up a lot. So DC-DC converter, power electronics controller, electric traction motor system, and everything is there. We already know. So when it's come to a battery, what is the primary role of the battery? So energy storage and delivery. So the battery pack stores the electrical energy and delivers it to the electric motors to drive the vehicle. That's the primary thing. So the energy conversion from stored electricity to mechanical power is what propels the vehicle to move forward. So the supporting role, okay, range determination. The capacity of the battery pack directly determines the vehicle range or how far it can travel with a single charge. So if you see the table mentioned over here, so the kilowatt battery size is mentioned and the weight is mentioned over there, and you can see the kilometers, right? So here the Mitsubishi IEMI EV 16 kilowatt hour battery which can only travel up to maximum 160 kilometers. Maximum 160 kilometers. Tesla Roadster, it's 53 kilowatt hours, which can go up to 390 kilometers. And BMW MINE, so that is going to go 35 kilowatt hours, but 240 kilometers. So these are reported ranges, right? So if you ask me, you buy a Tesla car, right? Fine, which is 53 kilowatts hour, and you want to drive 390 kilometers, I doubt it. The reason, because these tests are done under certain conditions, certain temperature, certain moisture level, maybe the AC is off, all the other components inside the car is off, just they are running it. So similar to a certain conditions only, it goes up to 390. So you set the AC, turn on the AC, set it to the 16 degrees Celsius, then you drive. You cannot expect the Tesla car to give 390 kilometers. It's not going to happen. So when they say these testing results, you cannot blindly follow these test results. Okay, I can charge, I can go for 400 kilometers without any problem. No, you cannot. So that is applicable for all the electronic devices, microelectronic devices, electrical devices, because the certain standards specify a certain condition to do the testing. For example, if I ask you, how many of you guys have iPhone or Samsung phone? Most of you guys might have it right now, right? So the Samsung and Apple, even Huawei, they advertise as they are waterproof. You can go to the swimming pool, jump in, you can surf, you can do all the sports activity, water sport activities, take photos and everything. It won't have any damage. So they say they have passed a certain IEC standard, which is for water resistant test, right? But if you try that one, you buy a new iPhone, you try that one and go to the Apple store. Like, let's say you try it out, taking a photo underneath a swimming pool, and you are trying to swim and just, do some activities. Then the phone got off, right? Then you go to the Apple store to check my phone is not working. What is going to happen really is they are going to open it up and they are going to check whether any water leakage is over there. If the water leakage is identified, that will not be covered under the warranty. It is mentioned in the warranty condition. So how they detect whether the iPhone is subjected to a water leakage? Because there are certain elements in the motherboard they have. When the moisture get into the motherboard area or water get into the motherboard area, that chemical becomes red or some change the color. So it's change the color and permanently stays as that color, right? So when they open it up, when they see the color change, they say, okay, you have put it into the thing. How come? They say it's water resistant up to 1 meter, right? But when you do this task and you bring it to the Apple store and say, I have a warranty, it's not working, they are not covering it. Why? Because the standard for that iPhone water resistant test is some numbers. I don't know. I can't remember. It's a nice standard. So where it mentioned as, check this one, okay? Under the temperature condition of 5 degrees Celsius water, the water temperature should be 5 degrees Celsius and the moisture level will be 27 to some 40 range. And the depth of the water should be 1 meter. So when you turn off the phone, put that phone under that water tank, like inside the water tank, which is 1 meter depth, leave it for 30 minutes, take it up without splashing the water, you dry it, then you turn on, that passes the water resistant test, right? 5 degrees Celsius water, moisture level 27 to somewhere around 40, I can't remember. And 30 minutes it need to be under the water, no splashes. And you have to turn it off. After turn on, dry, you have to take it out and dry it. After turning on, if it works, it passes the water test quality, resistant test quality. That's what they do. But finally, they advertise as they are going for surfing, they are going for sliding, they are doing water sports and everything. Finally, they test, okay, it's not covered under the warranty. Funny, right? Similarly, the car testing also like that. They promote it 390 kilometers, 400 kilometers with one battery full charge. But the conditions are unknown. It may be all that. I don't know what are the conditions. Maybe turn off the whole AC, no heater, no AC, just you close the windows and sweat. In the sweat you drive for full charge, you may be able to reach 400. So you cannot trust those stuff. These are not 100% sure, but this is a selling point that they do. So if you say I can drive for 400 kilometers, you will buy a car, Tesla, right? You can go for a longer distance, right? I can go from Colombo to maybe Polonnaruwa, Trincomalee, then I can come back with one charge. So, but it may not be true based on the condition. Maybe this 390 kilometer per hour. So you drive in a highway at a constant speed. Probably you can go 400 kilometers, but in reality, you cannot do that. You have to stop, you have to brake, and everything's adding on over here. This kilometer will reduce. At the same time, the aging of the batteries. How many cycles you have charged? Okay, I will show a graph how it's going to get reduced. All right. So these are the issues with this thing. So what are the challenges of battery recreation? If you see reduced driving range, definitely it's obviously all the Nissan Leaf. I'm taking it Nissan Leaf as an example because in Sri Lanka we have a lot of Nissan Leafs, right? Very few Teslas and other electric cars, but these Nissan Leafs are a lot, and their owners are struggling a lot, and they are not happy due to the issues that the battery is facing. So reduced driving range is one thing, loss of power and performance. So at the end, you will charge fully. Finally, the per mile cost might be equivalent to a fuel engine. Longer charging times, certainly it will take a longer charging time. Increased energy costs, thermal management challenges, yes. Decreased resale value, of course, that still happened, right, in the second-hand market. Still, the normal petrol engine cars goes more than 4 million rupees, where the AC Nissan Leaf go for 2 million still, right? Warranty and replacements are really big concern. So these are the issues of battery degradation. Okay. So when I said these thermal management challenges, this is an issue. So many cars got accident and it turned into like if the fire came up and the blasted, a lot of battery accident happened. So if you see Tesla cars, there are much more. The first car accident was happened and it became as a huge issue. Finally, Tesla said he was driving in a way where the road is full of stone, and the stone hit the battery and the battery heated up and it blasted. Later on, they put a protective case for that. So there is not only one case. There may be many cases available in the world. So if something happened, if is it reported to Tesla or any electric car company, they contact that person and say, we will give 10 million rupees. Don't release this news into the market. So like that, many of the cases are put under the carpet and we sealed it. Public doesn't know, right? So this is the world, how it works. Okay. All right. So now we will come into what is lithium ion battery. Okay. So lithium ion batteries are advanced energy storage devices that have revolutionized how we power a wide range of applications. At their core, these batteries function by shuttling lithium ions between the positive and the negative electrodes during charging and discharging cycles. This movement of the ion facilitates the storage and release of energy, making lithium ion batteries incredibly efficient and reliable. So compared to the lead acid battery that we have used in the past, this is super efficient because of these technology. And other important feature of the lithium ion battery is high energy density. So this means they can store a large amount of energy in relatively small and lightweight package. Compared to the lead acid battery, it's huge. You can open up and see. You can have a small pack with the same charge where same capacity where the lead acid battery can give. For example, compared to the traditional lead acid batteries, the lithium ion batteries are very small and it has the higher energy density. Another advantage of lithium ion batteries, their longer lifespan. Lead acid batteries, there are certain number of life cycle, but it's very less compared to the lithium ion batteries. For example, the Tesla car said the Tesla car can go up to maybe 300 to 400 kilometers for one cycle charge. At the same time, 1,500 cycles, charging cycles are possible. So earlier what we do in when it's come to petrol cars, we give, okay, 100,000 mileage or 10 years, right? 100,000 mileage or 10 years. When it's come to electric, the warranty period or 5 years. When it's come to electric cars, nowadays they say, okay, this many kilometers, 100,000 miles or 1,500 charging cycles or the age, right? So they rate the warranty period in that thing. So that is the long lifespan. They can charge it for 1,500 cycles charges, right? And maximum it can go up to 400 kilometers per one full charge. So these are the things that they market. The Tesla car is 1,500 as Elon Musk said. So in addition to their energy and lifespan benefits, lithium ion batteries also exhibit a high power density. So this means they can deliver a large amount of power quickly when needed. For example, when you want to accelerate quickly, it can give a high current output to pump up the motors. So this capability is critical in applications that require rapid bursts of energy. Example, accelerating the vehicle, right? So these are the advantages, right? When it's come to lithium ion batteries. So we use lithium ion batteries in mobile phones, electric cars, nowadays more or less all the equipments, right? Because of these benefits that we have. Size is smaller, energy density is higher, lifespan is higher. I'm using a Samsung phone. I bought it in 2018. Still, I use it. Still, the battery is good. It shows me 70% or something, right? Degraded, obviously degraded compared to the first brand new one, but it still is good because it uses a lithium ion battery, right? So due to these abilities of lithium ion, we selected these lithium ion batteries to put it into the car, right? If you ask me, in the video also they have said the battery technology is not new. It was there in 1925 before that. So they have using these lead acid batteries. I saw an old video where a car come, they remove the battery pack, put a new lead acid battery in, then they screw it up, then the car goes out. At the time, that was efficient. But later on, when the petrol cars, the gasoline electric engines, gas engines comes up, it took a more attention because of the benefits. Because battery car can go for a less distance, the lead acid batteries are not reliable that much. So then it went down, and again we started to gain the battery advancements due to the lithium ion batteries again. Tesla is not a new concept. It's an old one. It's a very old one, right? We have used it in 19. Our great grandparents have seen electric cars in the past, but now we are seeing EV everywhere. But there are issues with EV. We'll discuss those things. Let's shift our focus to a key term in our seminar, which is titled Remaining Useful Lifetime Estimation. We call it as RUL, right? And we will explore why it is so important to predict it accurately. So the remaining useful lifetime refers to the number of complete cycles a battery can undergo before it degrades to a point where it can no longer meet its performance requirements, right? So in our project, we define this threshold as 70% of the battery's initial capacity. So let's say the initial capacity is 100. So we get it to the 70%. That means get down and we say that is the lifetime of the battery. That's we define. So somebody can define it as 60. In our research, we defined it as 70. So this means that when the battery's capacity falls to 70% of what it was when new, it considered to have reached the end of its useful life, right? So to illustrate this concept, let's look at the diagram shown over here, which shows how the battery's percentage capacity varies over the number of charging cycles. Here we focus on the capacity degradation from 100% down to 70% in this particular research. There is no reference. You should use 70%. You can also consider 60%. But when it's come to mostly 70%, the battery started to perform really, really badly. Also, the graph is not perfectly linear here and contains some spikes here and there. You can see that the overall trend is going down, the reduction capacity, as the number of charging cycle increases. So as I said, according to Tesla, we have maximum 1500 charging cycles, right? So that means I not sure about how much is their threshold. They might say, okay, their batteries from 100% to 60%, it shows a really good performance. After 60, it started to degrade. So in that case, they claim 1500 charging cycles. Again, if you ask me, you can charge the car 1500 times again and you can use it in Tesla. I'm not sure, because these 1500 times of charging are under certain standard rules. If you take those rules and carefully look at it, it's not at all relevant to the real life scenario. So they say, according to this standard, 1500 times you can charge. But if you carefully study the standard, as I told for the mobile phone, 5 degrees Celsius water, who will get down into a swimming pool with 5 degrees Celsius cold water? Nobody. But the test is done under that condition, right? Similarly, that might be also a chance, but I'm not sure. Okay. So predicting the remaining lifetime is critical for several reasons. The first one, accurate remaining useful lifetime predictions enable the proactive maintenance and replacement planning, helping to avoid unexpected battery failures. One thing, this not only improves safety and reliability, but also ensures that the batteries are used to their fully maximum potential, maximizing their lifespan and efficiency. By knowing when a battery is likely to reach the end of its useful lifetime, we can better manage resources, reduce costs, and enhance overall system performance. So in a country, Hong Kong, I believe, professor told me something, the Professor Michael, I forgot the country. They have electric trucks in that country. When the truck performance started to reduce, they remove those battery, convert it into an auto rickshaw battery. They are changing the batteries without lifetime reduced battery into a auto rickshaw or three-wheeler to make it as an electric three-wheeler. So it runs because it's a lightweight with the capacity, it can perform a little bit. So it's a secondary thing. After the lifetime is reduced to a certain limit, then you change it to another vehicle. So secondary usage of the battery, that is going on all over there in the world. Okay, so the battery charging cycle with the capacity, it goes down here and there. There are some spikes. I don't know what's the reason it therefore. It's a data. Sometimes the data that you get record through the sensors are not always right. Right. So you have to clear the data before you analyze that thing. So now you know what is the remaining useful lifetime. So 70% mean it's dead. 100% is the brand new battery. So when you are charging 1500 times is the capacity, 1500 times you can charge and discharge. So that means, let's say a Tesla car is used for a certain number of cycles and you need to show you are going to buy that car. You have to estimate how many time is there that I can charge, right? So that is the thing, remaining useful lifetime on based on the charging cycle. How many time is remaining before it reaches 70% of the battery capacity, I can charge and run the Tesla car. So that is the remaining useful lifetime. So let's explore how we can predict the remaining useful lifetime of the batteries. Predict. There are generally two main approaches available when it's come to the prediction of remaining useful lifetime. One is model-based method. Other one is known as data-driven method. So we have taken the approach, the data-driven method, that is using AI, right? Artificial intelligence. As I said earlier, I am not a battery expert, right? I use the data of the battery, which is provided by Calci Lab, Professor Michaels, to do certain stuff on the battery management system, right? So one is this research, another one I will explain it very briefly at the end of this session, right? So if you take the model-based approaches, which use mathematical and physical models to stimulate the battery's behavior and degradation process. These models rely on detailed knowledge of batteries chemistry and operational conditions, enabling precise predictions under specific scenarios. Even certain simulation models like COMSOL or finite element COMSOL, MATLAB, they have these mathematical models built up for lithium ion batteries. But if you ask me how correct it is, I don't know. They are model-based battery based on the behavior of a lithium-ion battery. They have created a mathematical model which can act as a battery while we are doing simulation. However, the model-based methods can be quite costly because you have to done a lot of testing. You have to do a lot of testing to understand the battery performance and the characteristic while charging, while discharging, chemical reaction, everything needed to be studied. So developing a mathematical model is going to be really costly and computationally complex because you are going to solve a lot of parameters, matrices, and everything, and often tailored to specific battery models. That is true because if you take a lithium ion battery, this model, this thing, it's a different performance. And when it's come to another battery, another manufacturer, it might be a different performance. You cannot use the Philips battery to Kodak battery. It should have individual battery models developed for individual battery brands and types and the capacity, right? It's completely different. So one battery model, if you develop for a particular battery, that is going to only work for that battery. So this make the model-based prediction really complex, and it limits their general ability to test that in different type of batteries, which the rise of machine learning, right? With the rise of machine learning, the data-driven methods have become increasingly popular for prediction of remaining useful lifetime. These methods use data from the battery's operational history to train the AI model that can predict the remaining lifetime. Unlike model-based methods, data-driven approaches do not require extensive knowledge of battery chemistry or degradation process. Nothing. We just need to do couple of testing, charge, discharge, measure certain parameters like voltage, temperature, current, and certain things. With that data, we will be able to predict the remaining useful lifetime for any battery type, regardless of the manufacturer or type of the battery. But it's for lithium ion battery that we have done over here, but it can be any batteries, right? So, but the model need to be trained different batteries with different data. Okay. So instead, we do not want to study the chemistry of the battery. These AI models can learn from patterns in the historical data, making them more adaptable and often more cost effective because just we need a computer and some GPU power to do the training. In our case, we just had a small GPU, which is 3004 GB or something with that. And even you can do the training in a CPU machine. It's not computationally hard. But if you take a finite element modeling like COMSOL, you need a GPU. If you use a RAM, less RAM than 4 GB, the compute when you right away you open up the software, it's going to crash. So that means it's computationally hard to perform. So this shift towards data-driven methods have driven by the advances in machine learning, deep learning technology, now which allows more flexibility and scalable solution development for the remaining useful lifetime prediction. So in this project, we address the research gap by integrating memory features commonly used in language models, right? Let me think of a way to explain. Okay. So the generative AI, ChatGPT. ChatGPT is a large language model, right? So there are chatbots developed in the past before the ChatGPT came into the market. Those are chatbots used certain recurrent neural network technology. The memory feature is not embedded into it. For example, let's say you are talking about a cat, right? The AI model knows at the first context, the language model, you are talking about a cat. Then you ask a follow-up question where it sleeps. You are talking, okay, I have a, do you have a cat in your home? Like say I have a cat in my home. and I specify certain information about the cat and ask a follow-up question to the language model where the cat sleep. Then maybe it might be able to answer. But when you go to the third context, it loses all the memory. It will talk about something else completely wrong. For example, if you have a Siri, older Siri, I don't know about the new Siri, older Series, older Google Home, whatever, you just ask one command. A follow-up question is not entertained in that model. I have a Google Home. I can test it right now. Hey, Google, what's the time now? Hey, Google, no, it's not working. Yeah, anyway. So it just only say the time. Then you cannot ask a follow-up question because it do not keep the memory inside it. But in ChatGPT, you can ask a question, right? And you can ask follow-up question. It keep on adding the memory. Even after 30th question, you ask about the same thing instead of mentioning the cat, where it go outside for food, where it find the food outside. It still know you are talking about the cat, right? So that is the memory feature these large language models have. So how they do it actually? How they do it? They encode it. They encode it. Encode it means what? Basically, you are chatting about something. You ask a question to the chat GPT and it gives an answer. So now this conversation will be encoded into a certain summary. You summarize the confirmation. You ask a question, the chat GPT give like a lengthy paragraph as an output results. Before going to the next question, what it does is it summarizes your question and the answer it provided by the ChatGPT into a different format which has less memory, less context. It identify the certain information and it summarizes and keep it. When you ask the next question, it send this next question along with this summary of your previous question and the output is provided. It's a summary, not the whole context, right? Then the answer comes out because it knows what is the previous thing is about. Then the answer comes out. Again, it's a long answer, let's say. Now you have a previous summary and a new question and answer. What now happens is it keep this summary and get the certain key information from the summary and reduce the text and keep it as a memory. So when you ask the third question, it just go back along with this summary and with your query, then the GPT knows that you are talking about. So that's how these ChatGPT based chatbots are performing, right? We have worked on a couple of chatbots. You can go and check out the eSoft College of Engineering chatbots, right? I did some consultancy for them. So there, we have developed AI based chatbot. It does the same. We keep it in the cache memory. Until you chat, keep on doing, keep on going, it knows what you are talking about. You talk about a course, what is the price of this certain program? Then you talk about later, is there any holidays available or is there any payment option available? It knows you are talking about that particular program. But if you talk to Google Mini Siri, one question, it's gone. That's all. So in the earlier time, what they have done is they have used recurrent neural network methods to keep the memory, but it's a failure. But after this 2017, the transformer architecture released. That is the base thing for ChatGPT, right? That's the base thing for ChatGPT. After that, everyone started to use these memory features, encoding mechanism. So that's what we are going to do. Rather than saying, based on the historical data to the AI model, so these are the past historical data, learn from here. Based on this input-output relationship, estimate the remaining lifetime. More than saying that, you give the past couple of charging, discharging cycle as an input to the model and say, this is the memory, right? Now predict this is the last charging cycle and this is the previous memory. Based on this, predict the next remaining useful time will be more effective because it has the memory, past historical memory, right? Not only the historical data. LSTM, everyone knows it's a long short-term memory-based technique in AI, which is commonly very widely used for earlier language processing model before the ChatGPT came. After that, it started to use in prediction, forecasting, anomaly detection, those kind of approaches. So our AI model that we have developed using this architecture of this memory feature, and we have used the LSTM again, we have integrated both for the better performance, right? So our projects focus on three main objectives. The first one, selecting the optimal machine learning model for predicting the remaining useful lifetime of the lithium ion batteries. Second is integrating memory features into the model selected above. And the third, applying the model to predict the remaining useful lifetime of a Nissan Leaf battery modules, which is we have tested the module whether it's working correctly or not. I'll show the results. Those are interesting. So you might have seen the machines at service stations designed to measure the remaining useful lifetime of batteries. Yeah, if you go to a Nissan Leaf service center, they have a device which can estimate the remaining useful lifetime. Given that such machineries already exist, you might wonder why machine learning models are also needed to predict the remaining useful lifetime. Let's explore why machine learning methods are often better than the traditional approaches that the service centers use for their remaining useful lifetime prediction. Firstly, in terms of data utilization, traditional methods typically rely on a limited set of features such as voltage, mostly current. These methods might only provide a snapshot of battery health, that's all. But the machine learning methods, on the other hand, can incorporate a broader range of features, including voltage, current, temperature, internal impedance, and the past historical data of charging, discharging. So this comprehensive approach allows the machine learning models to make more informed and accurate predictions about the battery. Secondly, machine learning models excel at handling complex nonlinear relationship in data. That is good. That is really true. Traditional methods are usually simpler and may struggle to capture these intricate relationship between these data, which can lead to less accurate prediction. Machine learning algorithms, especially those designed for complex patterns, can better understand and model these nonlinear dynamics, improving the prediction accuracies. Thirdly, machine learning models are adaptive. They have the capability to continuously learn and improve as new data becomes available. So adaptive training, fine tuning, transfer learning. So there are multiple approaches available when it's come to AI domain. This means that over time, these models can refine their prediction based on the latest information. In contrast, traditional methods are generally static once deployed and do not automatically incorporate new data, which can limit their effectiveness as a battery technology and usage condition evolve, right? Finally, scalability is significant advantage of machine learning models. Traditional methods might face challenges when it's dealing with large data sets or extensive time series data, often working well only on the short-term readings. That is the thing the traditional method can work on. So which can make actually the prediction is not going non-accurate. Machine learning models, however, are designed to handle vast amounts of data efficiently. They can process extensive data set and time series data to provide more accurate and scalable remaining useful lifetime prediction. So these are the things. So the data utilization, model complexity, adaptability, and scalability, when it's come to ML models, they perform superior compared to the traditional methods that have been used currently in the market. So this is our overall methodology for the project that we have followed. For clarity, we have divided into 4 main selections. One is feature extraction, other one is feature fusion, other one is remaining useful prediction and application for real-time data. First, in feature extraction, we gathered data from the NASA official website to extract features separately for charging and discharging cycles. Why we have done it? I said we got the data from the Kelsey lab earlier, but we use the NASA data to train our model. The reason behind it, always there is a question asked. Okay, what we do in the traditional typical machine learning, you get the data set, divide it into training set, testing set, validation set, and you do the training, testing on the same data set, and you say, my model is accurate 90%. But the reviewers nowadays started to ask, researchers, it's from the same data set. How you make sure there are no replicated copies? So it can be simply like manipulated, right? The results can be simply manipulated if you are using the same data set for training, testing, and doing this thing. So I have seen a lot of researchers in many places, they say 99% accurate. So it's really hard to believe those things, right? Mainly based on the data. It is possible. It is possible. But if you ask me, it's going to perform 99% accurately in all the scenario. I'm not sure about that because you have trained and tested and validated in the same data set. So what we have done over here is we have used the NASA data set for the training part. While doing the training, the validation and the testing, we have used the NASA tester. Later on, we tested the train model on the Kelsey Lab data set and we obtained a really good result. So that's the approach that we have took. So the second section under the feature extraction and feature fusion, we combine these features to incorporate memory features into the neural network models, enhancing their predictive capabilities. In the remaining useful lifetime prediction section, we will discuss the models we have trained and the results obtained from each model. And the final section, we will see how the model performs when it's come to the real field test data. When discussing the data set, as I told you, we have used the NASA dataset, which is publicly available in the NASA website. So, which included the data from a commercially available lithium ion 18650 size rechargeable batteries. These batteries were subjected to 3 dicurrent operational profile, charge, discharge, and impedance, all conducted at room temperature 24 degrees Celsius. This is very important. When you are doing a testing, you have to mention the moisture level, the temperature level, under which condition it's performed this much. It's important. We have to do the same testing at that point to determine the remaining useful lifetime. Otherwise, the model may not perform as we expect because we are using the data which is trained and these data was collected on that particular condition. We are using that data to train the model. So that means when it's performing, the different condition testing might vary the results. So in here, you can see a plot of one typical complete charge and discharge cycle of a lithium ion battery. We plotted this graph using one cycle from the data set. The blue line represents the voltage curve, while the red line represents the current curve during both charging and discharging process. As in the plot, we can see that during charging process, the battery is charged at a constant current mode until it reaches 4.2 voltage, right? So for example, if I see here, it goes until 4.2 voltage. The current is constant current until it reaches the voltage. Once it hits this value, then the voltage keep constant while the current gradually started to reduce to almost zero when it's charged, right? So it's fully charged now. Throughout the discharging process, the battery discharges at a constant current rate 2 ampere. So we connected the load and we discharge it constant current pattern. This is how we have done the testing. So in the previous slide, we discussed on the graph plotted using a single cycle data. Now in this slide, let's look at these 6 graphs that we plotted using data sets from all available cycle for one lithium ion battery type. First 3 plots displays the voltage versus time. The first top 3 and basically it's voltage versus time, current versus time, and the temperature versus time. These are the curves. You can see there are multiple curves embedded into this thing. The bottom 3 plots shows the same parameters, voltage, current, and the temperature for the discharge. This is for the discharging cycle. This is for the discharging cycle. Let's focus on the first plot, which shows the charging voltage versus time over multiple cycles. According to the color index, the yellow color represents the initial cycles, which over here, you can see, which over here, right? And gradually changing to blue for cycles beyond 150. When the charging cycle is above 150, is becoming blue. In this plot, we can observe that the characteristic graph shifts from right to left along the time axis as charging continues. This indicates a reduction in the time required to reach the maximum voltage. A similar right to left shift can be seen in all 6 plots as the graph shown in the bottom. While it's discharging, you can see it's going here, right? So it reveals a clear pattern. By analyzing these behavioral patterns, we extracted features for both the charging and the discharging cycles separately. So after the pre-processing of the raw data, we got a lot of trash data over there. So we cleared them out. We extracted using the data processing. We got the clear data. After processing the raw data set, we extracted several features as mentioned in the previous slide. This slide highlights the features that exhibited a high correlation with the cycle count. So you know how the AI model is trained, right? You get a lot of features. Finally, you check the correlation in between these features. And finally, you select the maximum correlated features with the remaining useful lifetime thing. Then you use that for the training. You cannot use all the parameters because the model will be heavy and it takes a longer time. Maybe it might get confused while training. So we don't want to do that for the AI training. So we select the higher correlated matrices. For the charging process, we extracted the following key features. The first one is upper cutoff voltage time, constant current charging time, constant voltage charging time, maximum charging voltage, and maximum temperature and time versus time, area under the voltage curve, area under the current curve. So all these things are extracted for the charging, the features. For the discharging process, we extract the features including the discharging time, maximum discharging temperature, area under the curve, area under the voltage curve, and discharging capacity. So these are the main features that we have extracted for our AI model training. So this slides shows a correlation example matrix that we have determined with the charging cycle. And this is how we have selected the, in the Excel file, it shows how we prepare the data sets. It's a typical process when you want to do a machine learning model training. So in this slide, you can see the various models we trained throughout the project. We began by extracting key features from the data, which we then fed into 3 distinct types of machine learning models: a linear regression model, a support vector machine, and the deep neural network model, right? So commonly we call these as support vector machine as SVM, right? To evaluate these models, we measured their performance using the root mean square error, which is RMSE. That is a typical error that we try to compare the models in general. So we use that one. So the linear regression model produce an RMSE of 11.96. So RMSE less means it's a good model, which serve as a baseline for our comparison. So the support vector machine performed better, yielding an RMSE of 10.56%, indicating its ability to capture more complex patterns in the data. But however, when it comes to deep learning neural networks, DNN, which outperform both the SVM and the linear regression model, and it got the RMSE value 9.14. Less is better, right? So this lower RMSE demonstrates the deep neural network model superior in capability in predicting the remaining useful lifetime of the batteries. Given these results, we decided to move forward with the neural network model, deep neural network model, for the subsequent strategies of the project. So our next objective was to enhance the model further by incorporating the memory feature that I have talked about a couple of slides before, right, into the neural network. So this step was crucial in improving the accuracy of remaining useful line prediction, especially for capturing temporal dependencies in the data. So in the following slide, I'll go into more details about these memory features and their significance. But for now, it is important to highlight that we utilize 2 types of neural network in this phase. One is a deep neural network and a recurrent neural network. Especially when choosing the LSTM, long short-term memory, you can see over here, RNN1, right? Model, a specialized type of recurrent neural network for its ability to remember long-term dependencies compared to other typical traditional model. making it particular well suited for time series data like battery cycles. Not only that, solar energy forecasting, solar power generation forecasting, all the forecasting, LSTM is the hero up to the date now. There are certain time series forecasting released by the transformer model approach. They say, like ChatGPT, they released a model using the transformer based approach, trained that model in millions of time series data. It's a big model. They said this will forecast better compared to other traditional methods. But still, I have done a project for forecasting the revenue in a hotel in Dubai. Okay. So you, based on the previous historical data, you predict how much revenue I will make for next month, next week, tomorrow. We have tried several models. Finally, we have selected again the LSTM model because it's outperformed these transformer based architectures. LSTM is a superb model for forecasting. You can close your eyes, use it. Up to the date now, there is not a single better model than LSTM according to my experience, right? Which I have tried in the generative AI, sorry, not the transformer based approach, that the backbone of the generative AI they have trained is a large model, but still it's underperformed in certain categories. But LSTM is good, right? So we conducted experiments by training the deep neural network model twice. First with the memory features that were encoded, and then with the memory features with encoding, right? With and without encoding. The chart you can see here summarizes the parameters we used for deep neural network model. Each parameter was carefully tuned to optimize the model performance. We have done a lot of cycles of parameter fine tuning. The parameters highlighted in red indicates the best configuration that resulted from our fine-tuning process, leading to a most accurate prediction. This approach, through this combining various models and fine-tuning, allowed us to build a robust frame for accurately predicting the remaining useful lifetime of the batteries, setting the page for the application of these models in real-world scenarios, right? So we have done the experiments like this. So before we dive into the PCA encoder, we have used a PCA encoder to encode the memory. As I said, in the lang chain, in the ChatGPT generative AI, before we go to the second chat, we summarize it, identify the key information from that previous chat, and we analyze the summary with the second question. So then we know this guy is talking about this. So that's the typical process that the language model follows. We are going to do the same thing. So let's understand what memory features are. Typically, when predicting the current number of cycles that a battery undergoes during charging and discharging, we rely on present data. Maybe with LSTM, you can go up to little cycles, 5 previous data, only 5. However, adding a memory feature means that we are also considering a sequence of previous cycles data to predict the current cycle of the battery. So this approach, while common in language models, is relatively rare in remaining useful lifetime of the battery prediction. This is the thing that we have added as a new part into this project, right? When we incorporate memory features, the number of input data points to the model naturally increases, because what is going to happen? You are going to set the whole past input and the current testing results and put it into the model. So it has a large number of inputs. So if you have a large number of input, the model is going to suffer to do the prediction. So if you have large number of inputs, number of layers that you need and number of prediction layers, classification layers are going to be really high. Input layers are going to be really high. So we cannot have that part. So to incorporate these memory features, we combine the present cycles data. Present cycle data mean we do a testing, charging and discharging. That is the present cycle data with the previous number of cycle data to train our DNN model. So which expanded input data set when adding memory features, we needed an efficient way to manage the increased dimensionality. Because if you put as it is, what is going to happen? It's going to increase the memory size. The model is going to suffer in predicting. It's going to get loaded. So as language model do, in the previous chat history, it identify the key information and summarize it and keep it in the summary. and give it as an input when you're asking the next query, the same thing that we have done to reduce the dimensionality and summarize it. To address these, we used an encoding method to compress the input data, compress the input previous cycle data while retaining its essential key characteristics. That is important. Essential key characteristic. For this encoding process, we have utilized principal component analyzing PCA. PCA is an unsupervised machine learning technique that reduces the dimensionality of a data set while preserving as much variance as possible. It keeps the key information over there. It achieves these by transforming the original data into a new coordinate system, you can say new plane system, where the greater variance in the data is captured by the first principal component, the second greater variant by the second principal component, and so forth. This method helps simplify the data set. Large previous data set, we shrink it into a small data, simplified data set, making it easier to process and analyze without significant loss of information. This is the new thing we have embedded over here. So the flowchart shown over here illustrates the step we took to apply PCA in our project. The table below shows the which summarizes the number of features after encoding when considering different numbers of cycles as well as the accuracy of the encoder at each step. For instance, when n is equal to 1, we considered one previous cycle along with the present cycle. In this case, a total of 26 features, 13 from each cycle, were compressed into 8 features. 13, 26 features. By encoding, we reduce it to 8 features. That means we are summarizing, kind of doing the summarization. The plot you see here visualizes the effectiveness of the PCA encoding. The blue line represents the actual data, right? While the yellow line shows the data after encoding and subsequent decoding. You get it, right? After encoding and subsequent decoding, it's almost aligns with the blue line data. But 26 features reduced into 8 features, we encoded it and we process the data. When we use the encoding the data to decode it, it's again more or less mapping into the same curve. That means we are keeping the certain key information to reconstruct these data. But the features are limited from 26 to 8. That means we are reducing the thing, summarizing the model, keeping it as an input to the model. So that is the memory feature. So the accuracy of the encoder was measured by comparing the plots between the encoded and decoded features, demonstrating the effectiveness of our approach, preserving critical information despite of the data compression. So in this slide, we present the results and conclusion of our project. The table summarizes the performance of different models. When n is equal to 0, represent the deep neural network model without memory feature. And n is equal to 1 to n is equal to 4, represent the neural network model with memory features. Among the deep neural network with encoded memory features demonstrated the best accuracy at n is equal to 4. And the given plot shows the accuracy of the 3 models at n is equal to 4 stage, right? So in conclusion, this study presents a deep learning approach for predicting the remaining useful lifetime of the lithium-ion batteries of LIB cells through feature extraction from time series data and the evaluation of various machine learning techniques. We found that the deep learning network with memory features combined with a PCA encoder is the optimal solution. This approach not only enhances the prediction accuracy, but it's also applicable to higher capacity batteries as well. Right now, we have done it for smaller battery cell. It's not only limited to that. We can predict the larger battery cells as well, making it valuable method for battery management and maintenance and planning. So let's move into the next thing. So far, we have explored about models that we have developed and trained, and we have tested it in the data set. Now there's a time we have to test it in real data set, right? This brings us to a pivotal moment in our project. Now we are excited to show how our model performs when applied to a real world field data. To do this, we have selected a battery car module from Gen 01 Nissan Leaf. It's a real battery. The Nissan Leaf Gen 1 battery module is critical component of one of the pioneering electric vehicles in the market. still now, right? This module operates with a nominal voltage of 7.6 voltage and can reach one battery cell pack. It can reach a maximum voltage of 8.4 voltage. It features a 2P2S cell configuration, meaning it consists of two parallel pairs of cells, each pair arranged in series. This configuration allows the module to balance energy output and effectively and efficiently. The module offers the substantial capacity of 500 watt hour, making it capable of storing a significant amount of energy relative to its size. Additionally, it weighs 3.8 kilogram, which is relatively lightweight for its energy capacity, a factor that contributes to the overall efficiency and range of the vehicle. So the chemistry of the battery is lithium ion, a technology renowned that we have discussed in the past couple of slides, which is known for long cycle, long energy density, long power density, and everything, right? So that I don't want to repeat it again. So the decision to use this particular battery module for our field test was strategic, as it provides a real world challenge that our model must navigate far beyond the control environment of the laboratory. Why? Because we have used these models, we have selected the model, tested the thing, everything done in a laboratory under a certain moisture level, voltage level, and everything. When it's come to real time, we cannot maintain those stuff. So that's the challenge. By applying our model to this Nissan Leaf battery module, we aim to access its performance in predicting the remaining useful lifetime under practical everyday conditions. So this transition from lab-based testing to field data is crucial, as it allows us to evaluate how well our model can adapt to real-world variability and uncertainties, ensuring that it's not only theoretically sound but also practically reliable. So this is where the true test of our model begins, moving from prediction in control setting to real-world application and validation. So in this slide, you can see how we conducted the charging process for the Nissan Leaf battery module during our testing. So in the original test data, a constant current of 1.5 ampere was used to charge the battery from 2.7 voltage to 4.2 voltage earlier. Once the voltage reached 4.2, the voltage was held constant while the current gradually decreased to almost zero. That's the charging pattern that the NASA data was gathered. To replicate this process for Nissan Leaf battery module, which has a 2P2S configuration, meaning two parallel battery cells connected in series, we adjust the current to match the module specification. For our test, we charge the battery module using a constant current of 3 amperes, which carries 1.5 ampere through single cell, starting from 5.4 voltages and continuing until the voltage reaches 8.4 voltage, that is the maximum. Then we remove the constant current charging and we maintain the constant voltage, and the current started to decrease to come to zero. Similar to the original test data, how it's conducted, we have done it in the same way. This charging process was carried out in installation laboratory using these power supplies mentioned over here. This is the test setup. On the right hand side of this slide, you can see the user interface we developed to monitor and log data during the charging process. This interface played a crucial role in ensuring the accuracy and consistency of the data we collected. Two graphs below show how the current and the voltage varied throughout the charging process. When comparing these graphs with the test data graphs, we observed that the patterns are nearly identical between tested 18650 battery cell from the NASA dataset and the Nissan Leaf battery module that we have tested. You can see more or less the same pattern. This similarity indicates that our charging methodology was consistent with the original testing conditions, ensuring the reliability of our data for further analysis. So in this slide, we are presenting the process we used to discharge the Nissan Leaf battery module. After charging the battery to 8.4 voltage, and when the current becomes zero, we estimate that's fully charged. We used a constant current method for discharging. So in the NASA data set, they have deployed a constant current of 2 amperes to discharge each battery. Since the Nissan Leaf battery module consists of two parallel cells, to ensure that each cell handles a comparable load, we discharge using a constant current of 4 amperes. Until the battery discharges, the voltage drop down to 5.4 voltage. This discharging process was carried out in the microgrid laboratory of our university. And there is an electronic load which is capable of maintaining a constant current mode. We have used that electronic load mentioned over here, and we have discharged the thing. The photos above show the user interface provided by the equipment, the manufacturer, which we use for data logging and controlling the load during the discharging process. So this is the user interface for this device, this load. Okay. The blue graph illustrates how the voltage varied throughout the discharging process, while the red graph, if we have the constant current, it's anyway, it's going to be flat. After completing several full charging and discharging cycles, we extracted the key features from the data. These features were then used to predict the remaining useful lifetime of our battery module using our pre-trained model. Pre-trained model is NASA trained model, and we have tested it in the Calci data. That results is not mentioned over here, and it performed well. Now you are going to use it in your real-time environment. So during the charging and discharging process, we encountered several issues that affected our ability to accurately predict the remaining useful lifetime of the Nissan Leaf battery. These challenges led us to make some adjustments, including neglecting certain features and retaining the model before making our prediction. So we retrain the model by eliminating certain conditions, right? So we earlier considered certain conditions for the NASA data set, but when we try to consider this thing, actually it's not doing well. So we eliminated certain features. So one significant issue was with the temperature measurements. Since the tests were conducted in an air-conditioned laboratories, it was challenging to accurately account for a temperature deviation. As a result, we had to exclude the temperature data from the features used in the trained model. So we removed that temperature and we just did the training again, right? Because of the temperature variation of the control environment that we have did the charging and discharging in this thing. Additionally, we faced problems with power and network failures during the charging and the discharging phases. These issues affected our ability to capture accurate areas under the curve, which is crucial for precise data analysis. Consequently, we had to retrain the model, omitting the problematic areas under the curves. Another problem. After retraining the model, we proceeded with extracting features from the Nissan Leaf battery and predicting the RUL. At this stage, data normalization became essential. The main difference between the Nissan Leaf battery and the 18650 battery is the capacity, because they are only one battery cell. Here we have two battery cells in series, right? Series of battery. The 18650 battery has a standard capacity of 2 ampere hours, while the Gen 01 Nissan Leaf battery module has the capacity of 500 watts hours, right? So to address these differences, we normalized all the testing data for the training as well as for the testing, which arranges between 0 to 1. Normalization means setting all the data, maximum 1, minimum is 0, right? So the normalization was based on standardizing data for both batteries. That's a typical normalization process that we have done. The following calculation demonstrate how we perform this normalization before training the model and predicting the remaining useful lifetime of the model. So up to this point, the process involved in predicting the remaining useful lifetime of batteries have been complex and not easily manageable for the average person. To address this challenge and make our project more accessible and useful to the society, we decided to develop a user interface as well, which you are seeing right now. So in this slide, you can see the user interface we created for this purpose. Our goal with this interface was to enable anyone, regardless of their technical ability or background or familiarity with the coding and machine learning, to predict the remaining useful lifetime of the battery easily. We aim to make the process as straightforward and intuitive as possible. So the UI features two main tabs: plot curves and predict RUL. So the plot curve tab allows user to upload their charging and discharging data in an Excel file format. Once the data is uploaded, the tool generates plots for various key matrices, including time versus voltage, time versus current, and time versus power. So this functionality is designed to help users to visualize the performance of their batteries, making it easier to identify any potential issues or any anomalies. So here we have removed the temperature and the area under the curve due to the certain issues that we have faced while we do the testing for the Nissan Leaf. So predict RUL tab is divided into two subsections. One is feature extraction, other one is remaining useful lifetime estimation. In the feature extraction section, the users uploaded their charging and discharging data separately. By clicking the upload button, the system processes the data and extracts the relevant features. Once this extraction is complete, users can download a file containing the extracted features from the user interface. This file is then uploaded to the RUL estimation section. After pressing the predict button, the model generates and displays the remaining useful lifetime based on the extracted features. So the design of this interface ensures what user do not need any coding skill or any advanced technical knowledge to utilize it. In a car service center, a technical officer can do it without any issues. We have aimed to make this tool as user friendly as possible. They don't want even download, upload. So you just upload one time, everything is going to be extracted. Finally, the machine model remaining useful lifetime will be shown to you so that anyone can easily access and interpret the battery performance data. So we believe this interface will significantly enhance the usability of our project, making advanced battery analysis accessible for wider audience. So in this slide, we present a battery that we tested using our model. So this particular battery was removed from a Nissan Leaf vehicle, as I showed earlier. When the battery was taken out, the battery management system, BMS, indicated a remaining charging useful lifetime is 32%. The remaining charge of 32%. We then use our model to predict the remaining useful lifetime of the battery, and the model's prediction was 30.984%. So 32, the BMS system installed in the Nissan Leaf mentioning 32%. When it's come to our model detect as 30.984, which is very close, Where the Nissan Leaf, you can see the test report data over here, 32%. They don't know about the charging condition, the chemical and everything. They just check the traditional parameters. But our AI model exactly predicted 30.984. I would believe our model is better than the traditional thing, 32%, which is more or less closer. The close alignment between the BMS value of our model prediction demonstrates the effectiveness of our model in predicting remaining useful lifetime for the field data. This result highlights the accuracy and reliability of our model, showing that it can provide a near exact prediction of our battery's remaining lifetime in the real world data. Such precision is crucial for ensuring the longevity and optimal performance of batteries, particularly in application like electric vehicles. So there might be a question you can ask. I understand that someone of you might be wondering, if there is a model already to detect 32%, what is your model doing over there? That's a question obviously can come, right? There is already a BMS management system which is estimating the remaining useful lifetime in the percentage, 32. Then why we need our model? Of course, it's a valid question. The BMS is indeed crucial for monitoring and managing battery health while it's installed in the vehicle. However, when a battery is removed from the car, a key issue arises. All data stored in the BMS is erased and the system is reset. This particularly relevant when Nissan Leaf batteries are repurposed for energy storage system, such as those used in solar power installation. Once these batteries are taken out from the original vehicle and connected to a new system, the BMS data that could have provided insight into the battery health and usage history is no longer available. So this absence of historical data makes it challenging to accurately predict the remaining useful lifetime of these batteries with the traditional BMS system installed. This is where our model becomes essential. Unlike the traditional BMS, our model does not rely on the historical data stored in the battery management system. Instead, it uses the charging and discharging data for a couple of battery cycles to make the prediction. It doesn't matter where it's removed from, how long it has been used, we don't care. We know it's a lithium ion battery. We estimate the size. We calculate the charging and discharging voltage and the current, constant current for charging and discharging. And we do a couple of charging discharging cycles. That's all we need. We feed it into the train model. The train model will discharge. But the BMS, they estimate the time, but the BMS system cannot do that. This means that even after a battery is removed and no longer has access to its previous BMS data, our model still can access its RUL efficiently. Keep that in mind. There are cars for sale in Sri Lanka with replaced fake batteries. Fake batteries in sense, I say, those are not original. Different fake manufacturers, they wrap it with Nissan Leaf battery cover, send it over here. We believe that is true and original and we are installing, which are not. In that case, our model is needed to estimate the remaining useful lifetime of those fake batteries before you buy it. Makes sense, right? Now, BMS, just based on the installation, it keep the memory data and everything. Okay, how many charging is have gone through, how many discharging if I have gone through, then it has the data. Based on that charging, discharging data, it knows how many thing is remaining. But our thing, it doesn't want that because we have a model trained for lithium ion battery. Only thing going to vary is charging, discharging current. We have to estimate based on the capacity. Once it estimated, we do the testing. We get the data, we normalize it, put it into a model, then we get the output. So in this case, we can make sure, regardless of the BMS system, we can accurately predict this stuff. By applying our model, we can predict RUL of lithium-ion batteries models from Nissan Leaf Generation 1 cars at any point in any time, regardless of whether they are connected to a BMS or not. We don't care. The capability is especially useful for extending the life cycle and optimizing the performance of batteries that have been repurposed for new applications, such as removing a truck battery, put it into a three-wheeler battery. That is happening all over the world these days. That is must because you have to have a application. Otherwise, these batteries are going to be a huge waste for the world. As we suffer from plastic, we are going to suffer from these batteries in the future. You might have seen some images. These batteries are dumped at a place, right? So we have to use it for secondary purpose. So for that, we need to estimate how much BMS, right? So for that, our model is going to be used effectively. This capability is especially useful for these applications, as I mentioned, right? So our model provides a valuable tool for ensuring that these batteries are utilized efficiently and effectively even after their initial use in electric vehicles, secondary usage. And also before you going to buy a car, you don't know whether it's replaced with a new Nissan Leaf battery or not. And you don't know whether the guy got it from the Nissan company or secondary Chinese market, which they wrap it with the just fake battery, wrap it with the Nissan cover. We don't know. But our model is going to tell you these are the stuff. So these are the references that we have reading, and thank you for listening. I think let's see the time. Yeah, I think we are almost at the end of this timeline. So we will stop. I will talk about some other researches related to the battery if I get another chance, maybe in the future seminars if you want. But I would stop with these research. Now, if you have any questions, the floor is open for questions. You guys can ask the question. I'm more than happy to answer. Please let me know.
Thank you, Dr. Logeeshan, for that informative session. I believe that your insights have truly added depth to our participants' understanding of BMS algorithms, and your ability to simplify complex concepts is commendable. I believe the foundation that you have laid today is surely help our participants in their academic or professional journey. So as we move forward, we'd like to open the floor for a Q&A session. We invite you to raise any questions or doubts you may have about the content that was discussed today. I encourage all the participants to make the maximum out of this opportunity and ask questions and clarify doubts. To ensure that we have enough time to address as many questions as possible, we kindly ask you to keep your questions direct and to the point. You may raise your hand and I will call out your name, and then you may unmute and direct your question to keynote speaker, or you may use Zoom chat to ask your questions.
No questions? All clear? So am I that good lecturer to teach you without getting any question in your mind? Or else the guys not listening. This happens always in Zoom sessions. So please feel free to ask if you have any questions. So if you do not have any question at this moment, you always can go back to my research profile, Google Scholar. And in 2024, we have published a paper on this work in US, right, conference. So you can go through that leisurely, and we are working on a journal which will be published sooner. And yeah, so if you have any doubts, don't have right now, or didn't understand something that I have talked about, go and read those papers. You will get a clear idea. So while if you are going to do a testing like this, as we have done in our lab, you have to get the certification. Basically, the battery testing is very, very dangerous, right? So like it can pick up fire at any time. So it need to be done in a very safest way. What we have done in the lab, we know that battery is in a good condition and there is no one in the lab. We have done it in a table and we had all the fire extinguishers and everything nearby. So we were ready, right? So when you are going to do that, please make sure you have everything in your place. When it get fired, then you have to switch it off, right? And wear the protective measures and glasses and face shields while you are doing the testing, because testing a battery is always dangerous, regardless whether it's a good condition or bad thing. So, good evening, sir. I have a question regarding the discharge of the battery in Nissan Leaf. What methods you use to do the discharging of this battery? So, we have used an electronic load, which is in our microgrid lab, which is capable of discharging the batteries at a constant current. It's an electronic load. Okay. So, as I shown in the slide, so that we connected the battery, charged battery to that electronic load. Then we use discharge that. That's how we have discharged it. So while discharge, we recorded the current and the voltage, and we use that for our training as well. So discharging is through an electronic load, which is available in the microgrid lab of our thing. When you want to do it, you can also build up a simple thing. We can find a resistor which does not change its resistance when it's heat up. Then it's going to be continuous constant current, right? So, but we have used electronic load. Is that answered your question? We discharge it at 2 amperes. Yeah. Okay, sure. Sure, anytime. Made you dive into battery technology? Sir, what made you dive into battery technology? Was it something you had in mind while studying as an undergraduate, if you are involved in an engineering field? So that's an interesting question. So let me explain my journey, okay? So I graduated in electrical and electronics engineering degree. After that, I went to USA to do my PhD. That is in biomedical instrumentation. Biomedical instrumentation. So there I have developed working instruments and stuff, and I developed a sensor which is capable of diagnosing pancreatic cancer at its very early stage. Patented it. Right now it's under evaluation, FDA approval evaluation. Okay. So that is PhD. After coming here, I joined the electrical engineering department. There is no relation between electronics, instrumentation, and the research that I have done. I joined the electrical engineering, even though we had the biomedical engineering department in our university. So why I joined the electrical is the research that I have conducted in US. It will take another 50 years for me to do it in Sri Lanka. I cannot do it. If I go to biomedical engineering department, more or less, I will be forced to do a research in biomedical engineering because I'm in that department. So where I cannot conduct my research, which I have conducted in the US. So because that sensor itself costs $300 to manufacture one sensor, right? One gold sensor. Then $300 mean now 90,000 rupees. I have wasted more than 25 sensors to get the first successful results. So can you do it in Sri Lanka? No way, because we are a poor country, we cannot. And the technologies to fabricate that electrodes, not over here. It will take another 50 years to come to Sri Lanka. So that's why I joined the electrical engineering department. When I joined the electrical engineering, I had the instrumentation knowledge and certain AI knowledge that I have applied during my PhD. Then I started AI research in electrical engineering department, started to apply AI into power system, fault detection, predictive maintenance of generators, motors, bearings, all the electrical engineering domain I started to apply AI, right? Because of which I know is AI and instrumentation. So I need to do the research. Later on, battery is an electrical device, right? So I got to know a paper. I got a paper where it mentions it's a Professor Michael's paper where it mentioned as due to the voltage sensor and current sensor anomaly in the battery management system, a huge battery bank exploded in China because the sensor is showing the correct reading in the display SCADA system and the BMS also, and the current sensor is also showing the same normal reading. The BMS is estimating, okay, fine, battery is doing fine. What happened? The sensor is anomalized. It's not correct. So it's stuck at a point. It's not showing the correct value. The sensor went bad. So the BMS system couldn't do the maintenance properly. The battery exploded. I got that paper to read while I surfed through the internet. That made me interested. Okay, let's study that. What we can do by applying AI into these things. If I can do anything, that is the research that I have started collaborating with Professor Michael. Collaborating in sense he provided the data and we had clarified doubts and everything with calls. And he's a very nice person. He will attend any calls anytime, email. So contact him if you have any doubts related to battery. So that's the starting point. Then went to Calci lab and look at data in the battery. A lot of data available. So now we are doing certain researches how we can use this data and add a value to the BMS system. So this is going to be a part, can be a part of a BMS system, this lifetime estimation. And sensor anomaly detection, voltage current sensor anomaly detection should be a part of a BMS system because the BMS system is taking decision, making management based on the voltage and current data. If the data is wrong, the BMS system is going to perform completely wrong. So we have to make sure there is a system to monitor the voltage and current sensor data are correct before we feed it into the BMS system. So therefore, that is another part that in future it should be integrated into the BMS system. That is voltage sensor, current sensor, anomaly detection. That is the other research I will talk about if I get another chance. So that we have done. So like that, we are doing these research. So I was not fascinated about the battery from my undergraduate. I have multidisciplinary background. In US, there is not one department. All the departments collaboratively to work together in one research. In my in PhD research, there were 4 departments we are working together to achieve one goal. So that multidisciplinary approach. So that brings me into this battery research. So right now I'm doing battery research. There is no childhood thing that I have dreamed about that I want to do. Not like that. Okay. So what can be the causes for the spikes that came in the RUL? That I strongly believe due to the chemical reaction. I don't know actually. In the data, that is what it's shown over there. I don't know. Maybe a chemical reaction, because chemical, I can't understand what is happening. That's what I got with the voltage and current sensor data. So it might be due to some chemical reaction internally happening inside the battery. That might be the reason, I believe, but I'm not sure. Okay. Don't take my answers 100% correct, because I'm not sure, clearly mentioning. Okay. I'm not sure about that. Maybe that may be a reason. Okay. Other question. What is your perception on Chinese EVs? I feel like EV tech is more advanced now compared to Nissan Leaf technology. 100%. 100% agree. 100% agree. Chinese is evolving a lot in EV. They got 50% of EV manufacturing market all over the world. Rest of the world use altogether 50%. Chinese only one country, 50% battery manufacturing. They have put agreement with other Arabian, sorry, like South African countries to get the minerals for the battery. So they buy whole minerals from these African countries exported to China. So they are going to lead in the battery research, right? These EVs. But if you ask me how good quality they are in, I believe they will be very careful on that aspect. If one car exploded, US is waiting to capture that moment to market it all around the world. Our cars are better than Chinese car, because Chinese people give it for a very low cost. Tesla cannot do it because they maintain the highest standard. They are costly. Tesla car is costly. Right? It's a luxury model right now, having a Tesla car in US, right? So, but to avoid that, at least these Chinese cars are going to be, manufacturers are going to be very cautious on these reliability testing and everything, right? So they make sure they are not going to spoil their name. I believe the cars will be good. You can buy those cars because they are going to maintain a high standard in Chinese. They are going to rule the world in the future because 50% of the manufacturing is done in China. What can be the causes of spike? Okay, EVs compared to Nissan Leaf technology, that's an old one. Yeah, you are right. So there are much more. Chinese is going to take an advantage, and they are going to be a huge competitor for other EVs from the other part of the world. If I am to test the capacity of the used EV batteries for a project purpose, is it safe to charge and discharge battery to test the capacity? No. We have done it without a BMS in a lab setup. We have prepared all the fire protection and we put it for charging, and we were not nearby. We were standing away from it. We are monitoring these device data collection through our computer through an IoT setting. All the fire extinguishers are there. We are ready to do that. So it is not allowed for you to do this battery related testing without any precaution, right? You have to have all the equipments ready to face the accidents, right? Don't do it in home. Don't do it in a lab without any control environment. You have to have the safety measures, right? So I don't encourage, because Professor Michael has shown in his one of the keynote a lot of accidents, what happens while during the testing in their lab and in all around the world. So don't do it. And BMS system is good if you have it. Otherwise, it's dangerous. Thank you so much for the insights. I think that's all we cover. Okay, sir. How we can identify battery RUL without buying? Once we buying, I think we can refund this research for existing batteries. The thing is, before you buy a mechanical car, sorry, gasoline car, what do? You take it to a garage, let it examined by a person, expert person, and you buy it, right? You say he's okay, this is need to be replaced, this is giving a noise, this need to be replaced, these things are in good condition, you can buy it, estimated price is this much. The mechanic do it because they are experienced in that thing. So before you buy a Nissan Leaf car, you take it to the car manufacturer. If our model is coming as commercial model in the future, right? So the mechanic just remove one couple of battery cells here and there. You don't know to remove the whole battery cell, right? So you can remove couple of cells, or you can either We are normalizing the data, and you can keep it all the battery cells as it is and charge and discharge and normalize. That's fine. But the charging current, discharging current need to be in a different environment. Charge and discharge for a couple of cycles, right? Then use our model for the remaining useful lifetime. It will tell you what is the thing. But if the battery bank is not removed from the car, the BMS knows how many cycles it's we charged and discharged. So it knows. But in case of this changing thing, removing and putting it again, replacing the battery causes the issue because BMS doesn't know what is happening after that, right? So for that, you can use our models. Okay, then another thing. Okay, when conducting a discharge test on EV's battery, what specific precautions should be taken to ensure the accuracy and safety of the test, especially when spikes appear in remaining useful lifetime? Even we consider about if it's in warranty period or not. So testing the battery, as I said, I'm not a battery guy. We tested only one Nissan Leaf battery, but we have used the tested data from a controlled environment by NASA and Kelsey Lab. What I know is it's dangerous, right? When you do testing, don't do it without any precaution. Take a battery expert person who works on the battery, do it outside the lab, keep all the control environment, fire extinguisher, don't stay nearby, control everything manually, IoT based control. So it's always safe because I have seen a lot of accidents in the batteries. Even my laptop battery is swollen up. The mouse keypad that I'm using, it's here. The battery surface is here. The mouse pad is here because the battery pushed it up. I'm scared. I don't know when it's going to explode. Right? I'm going to China on Monday. I'm planning to buy a battery for cheap cost because it's very expensive. These batteries are in Sri Lanka nowadays. But still, I'm not sure in China whether they sell the original Dell battery or pack a Dell wrap in top of a fake battery. Nobody knows, right? So we have to be very careful. Testing related question. I'm not an expert on battery. As I said, I use the data to do certain things for the BMS system. That's all. Okay. So testing the battery, talk to a battery expert. As I know, it's very, very dangerous. Okay. In Nissan Leaf battery module prediction user interface available to the public of now? I don't know. Maybe there is a device you can simply connect and estimate it. It reads the remaining useful lifetime from the car, but I'm not sure whether the new cars have that for the public or not. Okay, so I hope I answered the questions. Again, I'm repeating, I'm not a battery expert, right? I use the data from the NASA and we are doing some manipulation and making some advanced module for the BMS, which should be integrated into the BMS in upcoming future scenarios, future cars. I'm not doing any testing. Only one testing. We took the battery module and we charge it in the thing. Other than I charge my phone and charge my laptop, I did this battery in the lab. I was very scared and I told my students to take all the precautions. They have taken it, right? We were ready with a fire gun to stop it, right? Stop the fire if it exploded. So don't do it in your home or anything. It's very, very dangerous. If you want, talk to a battery expert who are working on that. I think that's concludes the question and answering session. I hope everyone learned something today out of me related to the new addition for the BMS module. If you have any questions, please feel free to email me, right? I'll try to get back to you as soon as possible. Next 2 weeks, I'm not here in Sri Lanka. I'll be in China for a training session. After that, maybe I'll be able to reply. All right, Yasiru, over to you then.
Okay, I believe that's all the questions we have from the audience. Thank you, Dr. Logeeshan, for answering and clearing their doubts.
Pleasure.
Moving on, we would like to take a moment to express our gratitude to our esteemed speaker, Dr. Logeeshan Velmanikam, for accepting our invitation and sharing his valuable knowledge and expertise with us. So please, sir, accept our token of appreciation. Your
Thank you so
presence
much.
here has set a high standard for the caliber of learning we can expect from the workshop series. Thank you once again, sir.
Thank you. Thank you so much, guys. If you could send me this as a image or a certificate to my mail, I'll keep it. Thank you so much.
Okay. Right, before proceedings, let's take a group photo to remember this valuable time we spent together learning today. I kindly request the audience and the OC members to switch on your cameras to take a group photo. Please make sure to use the virtual background we have sent you in the meeting initiation.
Yeah. Before that, one thing I forgot to mention, I would like to thank the group members who have conducted the research under my supervision. So Samantha Mangala is the one who helped me to do this presentation, make this presentation and everything. So thank you for him as well. Yeah. Okay. Yeah, we can take the photo now.
Let's wait another few seconds till everyone's ready. Okay, I think we're good to go. All right, everyone, get ready. On the count of three, say cheese, right? Okay, 1, 2, 3, say cheese. Okay, let's make sure we capture a good shot. Are we good to go?
Yes, Zero. We can go.
Yeah, thank you, everybody. Also, please note that the quiz will be conducted on 5th of October into the workshop series. So also, we have shared a feedback form in the Zoom chat now. Also, you can scan the QR code on the screen to access the feedback form. We kindly request you to take a moment and fill it out. Your feedback is extremely important to us, and it helps us to continuously improve and provide you with better experience in the future. This is also considered for your attendance as well.
Okay,
Moving
Yasiru,
on,
then I will take a move.
yeah.
Bye, guys. Thank you. Nice meeting you, everyone. So see you in person whenever gets time. Okay. All right.
Okay, good
Bye-bye.
night, sir.
Yeah. Good night. Take care.
Moving on, the next session will be on 24th of August from 6 p.m. onwards, where Mr. Kasun Jalat from Vega Innovations will join us to take you through charging infrastructure innovations. As we near the end of the session, we sincerely hope that you find the workshop informative and thought-provoking, and that you leave with new insights and ideas. And with that, we conclude today's workshop. Thank you once again, and have a good night.